At the end of this video, you should be able to compare refracting telescopes and reflecting telescopes, and explain how telescopes for non-visible electromagnetic radiation differ from light telescopes. Chapter 26, Section 1, Telescopes. Our eyes can see detail, but some things are too small or too far away to see. Our ability to see the detail of distant objects in the sky began with the Italian scientist Galileo. In 1609, he heard of a device that used two lenses to make distant objects appear closer. He built one of the devices and turned it toward the sky. For the first time, he could see that there are craters on the moon and that the Milky Way is made of stars. An example of one of these early devices is shown on your screen now. A telescope is an instrument that collects electromagnetic radiation from the sky and concentrates it for better observation. While modern telescopes are able to collect and use invisible electromagnetic radiation, the first telescopes that were developed collected only visible light. Telescopes that collect only visible light are called optical telescopes. The two types of optical telescopes are refracting telescopes and reflecting telescopes. Refracting telescopes. Lenses are clear objects shaped to bend light in special ways. The bending of light by lenses is called refraction. Telescopes that use a set of lenses to gather and focus light from distant objects are called refracting telescopes. Refracting telescopes have an objective lens that bends light that passes through the lens and focuses the light to be magnified by an eyepiece, as is being shown on the screen now. One problem with refracting telescopes is that the lens focuses different colors of light at different distances. For example, if an object is in focus in red light, the object will appear out of focus in blue light. Another problem with refracting telescopes is that it is difficult to make very large lenses of the required strength and clarity. The amount of light collected from distant objects is limited by the size of the objective lens. Reflecting telescopes. In the mid-1600s, Isaac Newton solved the problem of color separation that resulted from the use of lenses. He invented the reflecting telescope, as is shown on the screen now, which used a curved mirror to gather and focus light from distant objects. When light enters a reflecting telescope, the light is reflected by a large curved mirror to a second mirror. The second mirror reflects the light to the eyepiece, which is a lens that magnifies and focuses the image. Unlike objective lenses in refracting telescopes, mirrors in reflecting telescopes can be made very large without affecting the quality of the image. Thus, reflecting telescopes can be much larger and can gather more light than refracting telescopes can. The largest reflecting telescopes are a pair called the Keck telescopes in Hawaii. Each telescope is 10 meters in diameter. Astronomers are tentatively planning to build an OWL, which stands for Overwhelmingly Large Telescope. That would be 100 meters in diameter. Telescopes for invisible electromagnetic radiation. Each type of electromagnetic radiation provides scientists with information about objects in space. Scientists have developed telescopes that detect invisible radiation. For example, a radiotelescope, such as the one shown on the screen now, detects radio waves. There are also telescopes that detect gamma rays, X-rays, and infrared rays. One problem with using telescopes to detect invisible electromagnetic radiation is that Earth's atmosphere acts as a shield against many forms of electromagnetic radiation. Water vapor can prevent gamma rays, X-rays, and most infrared and ultraviolet rays from reaching Earth's surface. So, ground-based telescopes that are used to study these forms of radiation work best at high elevation where the air is dry. But the only way to study many forms of radiation is from space. Space-based astronomy. While ground-based telescopes have been critical in helping astronomers learn about the universe, valuable information has also come from spacecraft. Spacecraft that contain telescopes and other instruments have been launched to investigate planets, stars, and other distant objects. In space, Earth's atmosphere cannot interfere with the detection of electromagnetic radiation. Space telescopes. The Hubble Space Telescope, shown on the screen now, is an example of a telescope that has been launched into space to collect electromagnetic radiation from objects in space. Another example, the Chandra X-ray Observatory, makes remarkably clear images using X-rays from objects in space, such as the remnants of exploded stars. The Compton Gamma Ray Observatory is no longer in space, but it detected gamma rays from objects such as black holes. The Spitzer Space Telescope was launched in 2003 to detect infrared radiation. The James Webb Space Telescope, launched in 2011, detects infrared radiation from objects in space. Other spacecraft. Since the early 1960s, spacecraft have been sent out of Earth's orbit to study other planets. Launched in 1977, the Voyager 1 and Voyager 2 spacecraft investigated Jupiter, Saturn, Uranus, and Neptune. These two spacecraft collected images of these planets and their moons. The Galileo spacecraft was in orbit around Jupiter and its moons from 1995 to 2003. This spacecraft gathered information about the composition of Jupiter's atmosphere and storm systems, which are several times larger than Earth's storm systems. The Cassini-Huygens spacecraft was launched in 1997, as shown on the screen now, and began orbiting Saturn in 2004. In December 2004, the Huygens probe detached from the Cassini orbiter to study the atmosphere and surface of Titan, which is Saturn's largest moon. Like Earth, Titan has an atmosphere that is rich in nitrogen. Scientists hope to learn more about the origins of Earth by studying Titan. Human space exploration. Spacecraft that carry only instruments and computers are described as robotic. These spacecraft can explore space and travel beyond the solar system. Crewed spacecraft, or those that carry humans, have never gone beyond Earth's moon. The first humans went into space in the 1960s. Between the year 1969 and 1972, NASA landed 12 people on the moon. Now, crewed space flights only orbit Earth. Flights, such as those aboard the space shuttles, allow people to release or repair satellites and to perform scientific experiments, like the one being shown on the screen now. Eventually, NASA would like to send people to explore Mars. However, such a voyage would be expensive, difficult, and dangerous. The loss of two space shuttles and their crews, the Challenger in 1986 and the Columbia in 2003, have focused public attention on the risks of human space exploration. Spin-offs of the space program. Space programs have brought benefits to areas outside of the field of astronomy. Satellites in orbit provide information about weather all over Earth. This information helps scientists make accurate weather predictions days in advance. Other satellites broadcast television signals from around the world or allow people to navigate cars and airplanes. Inventing ways to make objects smaller and lighter so that they can go to space has also led to improved electronics. These technological developments have been applied to radios, televisions, and other equipment. Even medical equipment has benefited from space programs. For example, heart pumps have been improved based on NASA's research on the flow of fluids through rockets. At this point, you should be able to compare refracting telescopes and reflecting telescopes, and Explain how telescopes for non-visible electromagnetic radiation differ from light telescopes.